Hello, in this video we're going to be talking about titration. Particularly I'm going to show you how to calculate the pH of a titration at some point, and I'm going to, with that, introduce something that I call a BARF table. Yes, you heard right, BARF table. Okay, so remember the titration basically is that you want to know the concentration of a sample. That is what we call the analyte. Of course, it's going to be unknown concentration, known volume. You're going to do it by reacting it with another substance that we call a titrant. For this one, you know the concentration, and because you're adding these in a stepwise fashion, you also get to know the volume to good precision. So concentration times volume gives you the number of moles. At some point, the equivalence point, the number of moles that you're adding of your titrant are going to be equal to the number of moles of your sample present. So you can determine the concentration of your original sample. That's the gist of how titrations work. Now, let's suppose that this is an acid-base type of titration. One of the questions that you can think about is, well, what is the pH of my solution as I continuously add titrant? So how the pH changes along that titration? Well, the take-home message here is that if I want to know that property of my system, what I need to pay attention is what is the composition of my flask, meaning what kind of a species I'm going to have at a certain point, and also recalculate the concentrations as I find appropriate. Because with the addition of the titrant, there's a reaction, moles change, but also the fact that you're adding titrant, the volume changes. So I need to calculate that, take into account that. Okay, first point, before you add any titrant. Well, in that case, the composition here is only whatever your analyte is. So it could be, for example, a strong acid or a strong base. It could be a weak acid or a weak base. And I know how to calculate the pH for that. There's no mystery. Just look at the composition and the concentrations. Now, once I start adding the titrant, I know that there's going to be a reaction going on. That reaction goes to completion. And again, since you're adding small amounts of your titrant, in principle, your titrant is going to be your limiting reactant all the way to the equivalence point. That means that the reactant gets fully consumed. It's going to react some amount of my sample, but that analyte doesn't react completely. It's the one in excess, not the reactant. So I'm still going to have some leftovers of my analyte, plus whatever products are formed from the reaction titrant analyte. Again, if it's an acid-base reaction, that product is going to be salt. The other one is water. Okay, at the equivalence point, the amounts of the titrants are equal to the amounts of the sample, so both of them are depleted. I don't have any of those in my system. The only thing that I have left, the composition of my mixture here, is whatever products came out from that reaction. In the case of neutralization reaction, that salt is going to be either giving me a solution with pH 7, higher than 7, or lower than 7. How that happens? If my species was a weak acid, the product is a conjugate base. So the pH at the equivalence point will have to be higher than 7. If, on the other hand, my analyte was a weak base, the product is a conjugate acid. So my pH is going to be lower than 7. That's how we can tell. Now, if this species was strong, it doesn't matter if it's an acid or a base, assuming that in all three cases, the titrant was a strong species. If this is a strong, then the salt is going to be a pH that, the salt is a product that gives me a solution with pH of 7. Now, past the equivalence point, you are just adding excess of your titrant. So the pH is going to be determined basically by that excess titrant that you're adding. Okay, let's go with one example, one of the many that you can have in that titration curve. And remember that the volume and the amounts constantly change. Because of that, we have to recalculate the concentrations. So instead of calculating concentrations at the beginning and then at the end, let's look at the concentrations, convert that into moles, and then just readjust the volume at the end to adjust the concentrations. Remember that volume times concentration gives me the amount. And I'm going to do that for both my sample, or analyte, and my titrant. So this is what I have here. For the acetic acid in this problem, concentration times volume, that gives me the amount. I'm working here with millimoles just for the simplicity of the calculations, and I do the same for my titrant. Now, look at these two values. One of them is smaller, in this case the titrant, and then that's going to be my limiting reactant. What does that mean? Since the reaction goes to completion, the limiting reactant is the one that gets completely used up. It forces some of my sample to react, but I have some left over, so my mixture is going to be now whatever analyte didn't react, plus the product. In this case, if it's a weak acid, my product is going to be a conjugate base. You always have to check for the stoichiometry here is 1 to 1, but don't forget to check stoichiometry. Now, how do I go about setting up this problem with the calculations? Well, a rice table is not necessarily good in this case because change in the rice table, the row for change is a variable. In this case, it is not. It's the actual number of moles of the titrant that I added. Here, we're going to use something that I call a BARF table. That's sort of a silly name, but hopefully, because of it's silly, it gets stuck in your head and it's easier for you to remember. How do we use it? Since we're not working with concentrations but with amounts, this BARF stands for amounts before action, amounts reacted, amounts final. Before action, what action? Well, before the actual reaction happens, I had this number of moles of my acid, this number of moles of my titrant. I determine that this is limiting reactant. This gets fully consumed, so that gives me at the end 0 moles of the titrant, but this one determines how many moles of the acid is going to be reactant and also constrain the number of moles of my product that can be formed. At the end of the day, what I need to worry about is what is the composition and also the concentration of those species in this final row in my BARF table. Look at the composition. I have a weak acid and its conjugate base. So that should ring the bell immediately for a buffer. And because the concentrations are the same, in this case for the 2 species, then the Henderson-Hasselbalch equation should be a good approximation to use. Let's bring it up. Now we have the pH equals pKa plus logarithm of the concentration of my conjugate base divided by the concentration of my acid. Now note that because in this case the amounts are the same, the volumes are also the same, both of them are on the same flask, then the concentration regardless is going to be equal. So it doesn't matter if I use moles or concentrations, at the end this ratio is equal to 1, log of 1 is 0, and then pH becomes equal to the pKa of my weak acid. That's another very special point that we actually studied during our lab this semester. Moles of the acid equals the moles of the conjugate base. That gives me pH equals pKa, and that corresponds to halfway the equivalence point. This is how I use a BARF table. Remember, I just want to use that in order to find the amounts that are left out after the reaction. With those amounts and the volume of the titrant plus the sample, I can recalculate the concentration, and because in this particular case I have an acid and its conjugate, that is a buffer system. Hopefully this helps clarifying what a BARF table is and when we use it instead of a rice table. But if you have any questions, please let me know, and I'll see you next time.